All right, welcome back to our deep dive into dynamic topology. So, in our last session, we built our most basic tool, right? The metric, our ruler for this mathematical universe. But a ruler isn't much good if all you're doing is measuring the distance between two tiny little dots. Today, we're going to learn how to measure entire regions. So, okay, we've got this ruler. It's great. It tells us the distance between point A and point B. But what about bigger stuff? What if you have a whole cloud of points or the gap between two galaxies of points? How do you measure that? Yeah, it's definitely time to upgrade our toolkit. And this is really where we take a pretty big conceptual jump. We're moving on from just measuring between two little individual points. Now we're starting to think about the properties of entire collections of points, or as mathematicians call them, sets. Yeah, this slide lays it out perfectly. It really gets to the core of our challenge today. Over on the left, that's what we know. That's our comfort zone, a ruler for 2 points. But on the right, that's the wild frontier, these big amorphous blobs of points. So the big questions are, how do we measure their internal size, and how do we measure the external gap between them? Okay, let's tackle that first one, measuring the inside of a set. So just imagine you're looking up at a cluster of stars, right? How would you describe its total spread with just a single number? What's that one measurement you could take that would tell someone how big that whole cluster is? Well, the most intuitive way seems pretty obvious, doesn't it? You just find the 2 points in that cloud that are the absolute farthest apart from each other, and then you'd measure the distance between them. That one number, that maximum spread. Well, that's exactly what topologists call the diameter of the set. And of course, there's a more formal, mathematical way to say this. The source text calls it the supremum, or the least upper bound. Now, that's just a really precise way to handle some kind of weird infinite sets. But honestly, for our purposes, and for pretty much any set you're going to run into, you can just think of it exactly like we said. It's the absolute maximum distance you can find between any 2 points in there. Now, I want to be clear. This isn't just a vocabulary lesson. The idea of diameter is actually a super critical key that unlocks way more advanced concepts. I mean, as Gordon Wyburn himself points out, you needed to define some really fundamental properties of spaces. And we're going to see a great example of that right now. Okay, check this out. This is a perfect example of why diameter is so important. This term, uniformly locally connected, yeah, it sounds pretty intimidating, I know, but it's a really crucial idea for understanding spaces that can be stretched and bent without tearing. The whole point is that no matter how much you zoom in, the space isn't all shredded or full of tiny holes. And how do you guarantee that mathematically? Well, you do it by putting a limit on the diameter of all those little local pieces. It's really our first glimpse of how these simple tools let us build incredibly powerful ideas. Okay, tool number 1, diameter, is in our toolkit. That's for measuring the inside of a set. So now for tool number 2, what about the empty space, the gap between two totally separate sets? How do we measure that? This is the second big measurement we need to nail down. We're not looking inside the sets anymore. Now we're looking at the space that keeps them apart. And the question is really simple. What's the absolute shortest bridge you could possibly build to get from one set to the other? And you guessed it, math has a precise term for this too. It's called the infimum, or the greatest lower bound. You can really think of it as the polar opposite of diameter. See, with diameter, we were searching for the longest possible distance inside a set. Here, we're searching through every possible pairing of points, one from each set, to find the absolute shortest one. It's literally the length of that shortest possible bridge. All right, let's just pause for a second and take stock here. We've just added 2 really powerful new tools to our collection. We've got diameter for measuring what's inside a set, and we have distance for measuring what's between sets. Seems simple enough, right? But why? Why are these 2 specific ideas so absolutely critical to the entire field of dynamic topology? Well, there's a great quote in the book's foreword from John L. Kelly. He says that Wyburn's whole approach is designed to get right to the very bones of the subject. And that's exactly what we're doing. We've just uncovered 2 of those bones, diameter and distance. These aren't just minor details. They're the foundational skeleton that everything else is going to be built on. And this is the really crucial takeaway. These are not just definitions you need to memorize for a quiz. They are fundamental building blocks. Seriously, think of them like Lego bricks. By itself, a single brick is pretty simple. But once you have them, you can start to build these incredibly intricate, powerful, and even beautiful mathematical structures. We can actually see the whole path of discovery laid out right in front of us now. Step 1 was establishing the metric. That was our basic ruler. Today, step 2, we use that ruler to create these two new tools for measuring sets. So what's next? Well, step 3 is using these new tools to define completely new properties of spaces. And that leads to step 4, using those properties to prove some major powerful theorems. It's just a really beautiful logical progression, one step at a time.
And that brings us to one last kind of provocative thought. Everything we've talked about today, diameter, distance between sets, it all works perfectly for sets that are just sitting there, frozen in place. But remember, this course isn't called static topology. It's called dynamic topology. The entire point is to study things that change, that move, that evolve. So what happens to all our nice, neat measurements when the sets themselves start to move?
That very question. How do we handle sets that are in motion? Well, that's our gateway to the next huge topic on our journey. We're going to be diving into the fascinating and really powerful concept of topological limits. Thanks so much for joining me for this part of the explainer, and I'll see you next time.